bumps and pushes. The power of the law of conservation of momentum goes well beyond the idea that a single object, with no forces acting on it, will keep moving at a constant velocity. When a force does act on an object, for example, by bumping into another object, the total momentum of the entire system remains conserved. Imagine we have two objects that are moving without any forces acting on them, such as two billiard balls on a frictionless table. A puck on an air hockey table is slightly more realistic, but any invocation of frictionless is going to be an idealization, much as physicists love to play that card. They are initially moving on straight lines, but then they collide and move apart on new straight trajectories. Let's label the initial momenta, plural of momentum, of the first ball as P1 initial and that of the second ball as P2 initial. Following an obvious pattern, we call the final momentum of the first ball P1 final and that of the second ball P2 final. Then the statement of conservation of momentum in this case is P1 initial plus P2 initial equal P1 final plus P2 final. The individual momenta clearly change as the ball ricochet off of each other, but the momentum of the system as a whole remains conserved. Momentum is always conserved, but we can forgive our predecessors for not noticing it right away. Think back to our Aristotelian coffee cup, which is at first motionless, then moves a bit when you push it, then comes to rise again when you stop. It looks like momentum is not conserved because the cup goes from zero velocity to non-zero velocity, but secretly the cup is reacting back on you, and your own body is pushing against the chair you are sitting in, which pushes against the earth itself. The change in momentum of the coffee cup is exactly compensated by a change in momentum in the other direction in the you, chair, earth system. You never notice because the mass of all that stuff is so enormously large that the change in velocity is unmeasurably small, though not quite zero. When you stop pushing and the cup comes to a stop, it is because the table it's sitting on has pushed back on it. And this time, the table or earth system gained back a little momentum, returning to where it was before you started pushing anything. In the film Gravity, there is a scene where Sandra Bullock and George Clooney are in peril, floating in their spacesuits outside a space station. Spoiler alert for this paragraph and the next. They are hanging on to the station by a single tether. In an otherwise delightful movie, the physics in this scene gets a bit wonky. What we see is that Bullock has to hold on for dear life as Clooney is being pulled away from her. In reality, since they are all in pretty much the same orbit around the Earth, there would be no forces pulling them away from the station. A gentle tug on the tether would bring them home safely. But in the movie, she has to let go of him to allow herself to return. I don't object when filmmakers bend the law of physics a bit in the service of a good story, but in this case, the bending was unnecessary. All you had to do to concoct an equally dramatic scene was to eliminate the tether entirely. Imagine that Bullock and Clooney had been holding on to each other but floating slowly away from the station with nothing connecting them to it at all. Conservation of momentum will tell them exactly what to do. If they stay together, they would have drifted inexorably away, and eventually both would die. But there's another option. One of them could have pushed the other one away. Their total momentum would be unchanged, but one of them could have drifted back toward the station while the other moved away even faster. Clooney could have sacrificed himself by pushing Bullock back home. Or either Clooney or Bullock could have saved themselves by pushing the other away to an inevitable doom. But that would have been a different movie.